All right. Can you hear me, first of all? Okay. It's a pleasure to be here. I'm really pleased that Joe is now old enough that we can celebrate him. And I'm going to talk about field theories of quantum critical metals. You've all seen this kind of picture. I'm not going to explain what it's supposed to represent. Most of what I say will be review, a lot of it review of work of actually Joe's and others who did similar things at the same time. But to the extent I say anything new, it'll be based on work done with two colleagues at Stanford, Kibelson and Raghu, who are both faculty members there, and Liam Fitzpatrick, a spectacular postdoc, and Jared Kaplan, who just left for Johns Hopkins. Okay, now, I thought coming in that I would be giving an awkward talk that didn't seem fit for the occasion, since we, of course, all know that Joe is a wild-eyed quantum gravitationalist at heart, and I'm talking about condensed matter physics. But luckily, John Preskill already mentioned some of Joe's central work from the early 90s, and then Matthew, in the last talk, discussed their fruitful collaborations from that period, too. I first met Joe at TASI 22 years ago. He and Jeff Harvey were directing the school and forcing us to play volleyball with Nazi-like intensity. But he also deigns to discuss physics now and then. Because the string theory community was fixated on black holes in 2 dimensions at the time, Joe decided to go in a totally different direction. And he talked about the effective field theory of the Fermi surface in his TASI lectures. His goal, I guess, was aimed at first educating a bunch of string theorists that you can use effective field theory, a point many of us still often forget. And then also that there are interesting problems using field theory, even in domains as far away as maybe the fun mysteries of high TC. And these lectures are actually now a standard reference for this approach to Fermi liquid theory, along with a contemporaneous paper of Shunker's. Now, much later in 2001, I was lucky enough to co-organize a program here. And I collaborated with Joe and with Steve Giddings on a paper. The details were about flux compactification and string theory and warped geometry. It all sounds very early 2000s to me. But anyway, the consequences of this paper were that roughly for 5 years, the directions of my research went in trying to figure out the mathematics of those compactifications and whether they could be related to cosmology with Let Me Learn About Inflation. And finally, I was drawing pictures like this in my talks, especially if David was going to be in the audience. But really, that collaboration was a tremendous learning experience for me. It's hard to overstate how important that collaboration was. And my interactions with Joe and the Santa Barbara group, except David, over that period, were tremendously fruitful and educational. Okay, now let me get back to the problem I'm talking about today. This is a mixed audience. Most of you probably, I hear Nima said it explicitly yesterday, you don't care about metals. But let me tell you what I'm studying. So I'm studying metals. They're well described, in many cases, at least this is what we're taught in basic courses, by an adiabatic modification of a free electron model. Okay, this is the adiabatic hypothesis that goes into Fermi liquid theory. So the basic picture you should have as a metal is like a box. You all know the particle in a box eigenfunctions in quantum mechanics are these waves, signs with various momenta. And so you fill up the more and more excited states in the box till you've reached the electron number that you want. And you get a sphere in momentum space, the Fermi surface. And then fairly robustly, this picture determines a lot of striking physics of these substances. For instance, only a thin shell of states right near the top of the Fermi surface can be excited by a small temperature. So things like specific heat scale with T, a more detailed but still pretty elementary calculation can give you a hand-waving argument that resistivities should go like T squared. And this is really something you teach juniors in stat mech. Now, there are settings in modern materials. I'm not the right person to tell you about them. Many people in Santa Barbara understand the real details of the lattice physics and what the material is better than me. But there are definitely settings in some of the most interesting materials where this breaks down. And that leads to a question for theorists, okay, who don't necessarily know about the materials. The picture is supposed to be in these materials. Here's a famous picture. There can be an interesting phase that exhibits non-Fermi liquid behavior, meaning not governed by those exponents, over some kind of dome, maybe of superconductivity. And then, for instance, the resistivity, this is stolen from Joe's 92 paper, other than a little offset, can be linear over a wide range of temperatures. Now, the point of Joe's lectures then, and a point that still holds force today, is that that's hard to incorporate in the minimal effective theory that governs these systems. So let's start with Joe's theory, Landau's Fermi liquid theory, a la him and Shunker. and then see where we have to go. Okay, so the basic picture that Joe advocated, this again is stolen from his paper, is that here's the Fermi surface, and the excitations consist of little electrons with momentum a little above the filled states, or holes in the filled Fermi sea. So we start with the free action that we'd all write down, psi dagger dt psi. There's some energy dispersion, and you should subtract off the Fermi energy because all those states are filled. Okay, and that gives you that picture of the sphere in momentum space. Now, what about interactions? If we're going to find interesting phenomena, right, really exciting things that could explain, for instance, that picture, then interactions ought to be important at some level. Well, what Joe did is say, let's study a renormalization group and see if this free theory that we started with, the one that's sort of boring, is stable or not. And if it's unstable, the instabilities tell us what exciting things could happen. Now, the RG he set up is a bit unusual for high-energy theorists because you don't scale towards zero momentum. Instead, you take the Fermi fields at some momentum and you scale them towards the Fermi surface. Okay, so the black thing here is the Fermi surface. The red band is the low-energy states. Light blue is higher-energy states you've integrated out. And you write momenta as being some vector on the Fermi surface, k, plus an orthogonal vector, L. You can always do this, okay, unless we consider really pathological Fermi surfaces. And then you scale so that the energy is basically just governed by this orthogonal component times the Fermi velocity. And the scaling then is like this. K doesn't scale, the transverse momentum scales, and so forth. So you then go back, you require that this free action be marginal. That tells you the dimension of psi. So the question, the interesting question, at the time, actually, I remember when I asked Joe why he wasn't working on string theory, and he was working at high TC, he said, Weinberg just got a $2 million chair at Texas, and I really want to be paid as much as Weinberg. And he thought if he solved this problem, that would get him a $2 million chair. Anyway, so what dangerous terms could arise to destabilize the Fermi liquid? Well, you said it. One thing that could happen is that mu could be shifted. Okay? In other words, E Fermi is getting corrected by some divergent terms. No problem. We didn't assume a special shape of the Fermi surface. If we do later, it'll be based on discrete symmetries that are easily preserved under radiative corrections. So this is not a problem for us. It's relevant, but we don't make assumptions about its value. It's not like the Higgs mass. Now, the leading possible interactions, then, that respect all the symmetries in the problem that we, spin, rotations, and electron number, involve four Fermi operators like this. Psi dagger psi, psi dagger psi. And you just do the scaling that was on the previous transparency, you'll find that these naively scale to zero as S. And so the theory is completely stable, and life is very boring, and everything should be this free fermion picture. Now, that's too quick. It's too quick because in saying that, I assume that this delta function has trivial scaling. The momenta at different points on the Fermi surface are arranged so that in the cancellation in the delta function, only components of the momentum that don't scale, the big kf-like component, are relevant. But in fact, for special configurations, for instance, fermions at antipodal points on the Fermi surface that scatter to a pair at other antipodal points on the Fermi surface, the delta function scales. It's an elementary argument. I'm not going to try and go through it in more detail here, but you can convince yourself that then some of the small perpendicular components that scale enter in the delta function in an important way, and it scales like 1 over s, yielding a marginal operator. And then Joe taught us that just like in QCD, where we've learned that a marginal operator can grow strong in the infrared and lead to interesting physics, here's the marginal operator. It could grow strong in the infrared. That depends on the sign of the 4 Fermi term. And it could lead to interesting physics. And that interesting physics was already discussed in the 50s. It's the BCS theory. That's the only instability of the fixed point that he could find. Now, what that means to me is that the standard theory can't explain non-Fermi liquid scalings. Okay, so what can you add? In particle physics, when we have such a situation, we can add 6 extra dimensions or double the number of fields or whatever else. But condensed matter physicists seem to be more conservative than that. So what else actually happens in the systems? Well, the systems exhibit phase transitions. For instance, there's debate now about whether there's hints about nematic order under the dome and cuprates. There's obviously magnetic ordering in these systems in some parts of the phase diagram. So it's natural, and not at all a stretch, to add a bosonic order parameter field. So what we and others have been doing for many years, actually, is trying to understand interesting behaviors in this very simple modification of Joe's theory This L psi is exactly the theory he studied. And L phi adds just a scalar field with a mass that will tune to 0 at criticality, some velocity c, which can be different from the Fermi velocity v. This is not a relativistic system. And then a quartic coupling. And the bosons and fermions, so as stated, this is, of course, two decoupled theories, but they should be coupled by a Yukawa function. And here's the Yukawa function. It's generally a function of k and q. For the nematic problem, it should vary in this way. So there are some cold spots on the Fermi surface where it vanishes. For a ferromagnet, there would be some spin matrices here, and g could be constant. OK, we could decide what problem precisely. So our question is, can the addition of the bosonic order parameter to the story lead to interesting new approximate fixed points that could govern physics above a dome? Okay? And the word approximate is important for me. And something else that will be important for me is to have small parameters that control any statement that I make. Okay, so now there's a basic conflict in this coupled system. The way Bob Laughlin likes to say this is it leads to a titanic struggle between bosonic and fermionic degrees of freedom. Why does that happen? Well, the fermions can damp the bosons. Intuitively, that means on shell, a boson could try to decay into a fermion pair. That would be cutting this diagram in half. This is the one loop diagram that corrects the boson propagator. And meanwhile, the bosons do something really interesting. If they have interesting properties themselves and they correct the fermion self-energy, then you can get a non-Fermi liquid. And so the game here is to try and find regimes where you can really determine the outcome of this kind of struggle. There's a standard approach to this, really built up, well, Hertz's paper is 1976 and Millis is 1993. So for about 20 years, a sort of standard approach has been something called Hertz-Millis theory. I'm not going to do this, but let me tell you very quickly what it is. So you first compute this diagram. What you'll find, because it's a non-relativistic system, you get expressions that look very odd to people like us who are string theorists. You'll find a correction that scales in this way with an omega over q type correction to the kinetic term, and then the old q squared terms. And the typical analysis then says, well, look, omega over q at low energy for the boson is more important than omega squared. So we're going to re-expand the theory, keeping omega over q as the dominant term. That's an interesting idea. Okay, I don't think it's a perturbative idea. It's an uncontrolled guess in a certain sense, but it's an interesting idea. If you extrapolate that to very low energies, you do what I just said, and you feed it back into the fermion, you'll find some kind of non-Fermi liquid. Okay, and there's a long line of work building in this direction by many distinguished people, Hertz and Millis. Joe did some beautiful work on this at large number of fermionic flavors, where it's best justified in '94. Many other people in Santa Barbara have thought about this. That's fine as far as it goes. I want very small parameters, which maybe large NF could provide. But I'm going to go in a different direction. So what we've set out to do is systematic perturbation theory about the ultraviolet, okay, the analog of what was done in just in Yang-Mills theories, and look for non-Fermi liquid fixed points or even intermediate scaling regimes that we think we can reliably access in that way. So our goal will be to have some parameters. Sometimes it will be n, sometimes something more interesting. Sometimes we'll just say g is small, that tell us that over a range of energies between the cutoff, they tend to call that E Fermi, so that's M Planck for you. And somewhere between E Fermi and some low scale, we'll try to figure out what fixed point matters. At this low scale, the way I'll define the low scale, where I stop telling you what happens, will be by telling you the scale at which some effect analogous to this will become so important that I don't trust my analysis anymore. Okay, so I'm doing a self-consistent perturbation theory. Now, this will usually lead to a breakdown at some very low energy, but in a problem that was motivated, at least for me, by trying to understand behavior over an infrared dome, I don't really care. Okay, so that's just fine. I just want to tell you what happens. So here's the analysis we've done. We wrote a few papers. Some use large N, but not the large N that Joe used, in which he did a very interesting analysis at large NF. The large N we use is more analogous to the one that you know from ADS-CFT. It has a large N matrix boson. Now, condensed matter physicists don't like that. So a more interesting parameter is the ratio of velocities, V to C, of the fermion to the boson. We'll treat that as a small parameter, and we'll see that that's very self-consistent, because in the flow equations, we get V actually flows to be small. Okay? So it's a hypothesis that's self-consistent. So the theory we're perturbing is then this one that I already told you. It has an upper critical dimension of 3 plus 1, Why? Well, the quartic interaction you all know is marginal in 3 plus 1. And this Fermi-Lagrangian, when you add the Yukawa coupling to the boson, which I just erased on this slide, unfortunately, that also has an upper critical dimension of 3 plus 1. Okay. So we're going to study it in the epsilon expansion. And in perturbation theory, well, in G, the Yukawa coupling, and with 2 additional handles. Okay, and the 2 additional handles, I told you, we could consider a matrix large N boson. The boson self-interactions would a priori cause a problem. After all, we can't solve pure glue QCD at large N. But with this particular problem, we don't care about the boson self-interactions so much. And it turns out that there is a way to treat the bosons that's radiatively stable such that they give an ON squared Wilson-Fisher-like model if you just consider self-interactions. Okay, so this is not something you can do with the gauge problem. The second small parameter is this ratio of velocities. The system is non-relativistic. There's a fermion velocity V and a boson velocity C. And we'll see that the ratio V over C can serve as a small parameter, even down to N equals 1. Okay, and really, I'll focus on this one because my colleagues in McCullough at Stanford don't like this one. Okay, but I'll mention N when relevant. If you're somebody who wants parametric control and you really want to know what happens, you can take N to be 72 and you'll feel much better. Okay, now the boson self-energy can be evaluated in some standard way. You can look this up in a book by Fedor and Wleczka or something from the 60s. Here's the answer. Okay, this is called a Lindhard function. You see that there's a complicated dressing in the boson self-energy due to the fermions. And the important point here, and the one that should give you some intuition, is that when the bosons are fast, meaning C is much bigger than V, then at least for close to on-shell bosons, this thing is purely real, which reflects the fact that the bosons can't decay. Okay, the very phrase Landau damping is talking about the damping term, and that's really far from true, at least for on-shell bosons in that regime. In fact, you can show analytically that in the small V over C limit, the leading behavior of the self-energy for the bosons is proportional to V, with a ratio of energies to momenta that you normally take as fixed in some limit. So it vanishes as V goes to 0. That indicates that if there's some scale of breakdown where non-local terms seem to be modifying our analysis, small v should broaden the energy range where we can tell you what really happens reliably. Okay, that is, the bosonic dressing of the fermions should dominate over Landau damping at small v. Now, matrix large N would only help any such statement. The Landau damping is then a 1 over N effect. So I'll just analyze the N equals 1 theory. So now what we do is just a basic RG, starting with Joe's scaling in the fermion problem, literally taken from his 1992 lecture notes. So this is the fermion scaling. It scales towards that band. Here's the boson. The boson scales to the origin. It's like Wilson-Fisher, and we're doing perturbation theory. That's all that we can do if we want to do perturbation theory. So the basic processes in this effective theory is a fermion a little below the Fermi C gets kicked up by a boson of momentum Q. So I've set up the problem for you. I'm not going to go through calculation of numerous loop diagrams. I have colleagues who are very skilled and can do this, and I trust them. Okay? But you derive these RG equations by decimating in energies and momenta in the loop-corrected action, and you get a system of equations that looks like the following. The boson velocity does not flow. The fermion loop diagram is, in fact, UV finite. That's related to the non-relativistic nature of the system. These coefficients were computed probably by Matthew's father. The bosons flow to a Wilson-Fisher fixed point with G not perturbing the flow at this leading order. But the other parameters flow in a much more interesting way. The fermion velocity gets a flow correction of order G squared with no epsilon in the epsilon expansion, times a function that at large enough V, I'll tell you what I mean by large enough, it doesn't have to be very large, is just 1. At small v, there's a more complicated behavior that involves another parameter W. Okay. But it's running towards 0. G runs in this way. It has a stable fixed point. And this new operator W that I'm introducing for the first time in these equations, and that I'll tell you what it is on the next slide, runs irrelevant by order 1. But it's going to become important because although it's formally irrelevant, V is running to 0. And when the leading term runs towards 0, you have to worry about a crossover where the next subleading term competes. So here W is a new parameter that we introduced, and it's exactly what I said. If you look at the dispersion, there's this VL from Joe's paper. there would a priori be a WL squared term where W is tiny. It's of order some cutoff, right? But if V really does flow to 0, there's a very low energy at which the two compete, and where you have to modify the story. Yeah. Yeah, it's absolutely going to 0, but take a look at the equations. You see that V is actually running towards 0 in a pretty striking way, which is the same way in which you get a Landau pole. That is, it actually hits 0 in finite RG time, whereas the running of W is proportional to W. Okay, so this Landau pole-like running is crucial. Now, because of that, Joe's question was basically, how can any perturbative correction beat an order 1 irrelevant operator in terms of flow towards 0? And the answer is, you actually know a case where this happens, the Landau pole. Okay, so this beta function is of that form. Because of that, here's the flow diagrams. Here's epsilon equals 0. You flow towards the trivial fixed point, but very low V. And here's some tiny value of epsilon in the epsilon expansion. You flow to the non-trivial fixed point for the fermions, and you see V is going towards 0 rather rapidly. Yeah, so I didn't talk about this function S, but at the origin, it's a smooth function that changes sign in the right way. So yeah, there's no discontinuity in S, and V doesn't keep running negative. There's a symmetry. Say again? It has a term that first starts independent of V. But when V and W both go to 0 in the right way, it's just some smooth function that goes through 0 at 0. Okay. So here's the important point. V over C is flowing towards 0. Okay, that's the only thing I wanted you to take away from those graphs. So maybe we made a mistake in the RG. If we didn't make a mistake in the RG, V flows towards 0. Now, as small v acts in some sense as a control parameter, because damping contributions that we can't control are proportional to V, this can prevent boson decay from being important, and that's physically interesting. It's not some formal statement. Now, the question that you have to ask is the analysis under control? Here's a reasonably conservative control criterion. You could have other ones. It would be to say that the analysis breaks down at a scale that's defined when the correction due to Landau damping, that's pi, the self-energy, is of order the same as the tree-level propagator. Okay? That means G, the effective G is no longer smaller than 1. Okay? Here, X is the ratio Q0 over CQ. Now, you might wonder what value of X to take. What we did is the conservative thing. We defined mu by being the value where if you maximize this expression with respect to X, you get 1. Okay, so it's the most conservative thing you could do. A more reasonable thing might be to take X to be on shell. So you get some kind of broad swath in parameter space where the analysis is controlled. This white region here should really be shaded. It's not for a technical reason that I'm happy to answer for anyone who wants to know, but things get better and better at small v. And the shaded region is where that criterion is satisfied. Okay? In other words, small v and reasonably small g. This is n equals 1 for matrix large n. The contours get better. Yeah. Say again? No, as I said, this shaded region, this region should really be shaded. And I'm about to tell you why it's not, because something interesting happens before you quite get to 0. Okay. See, in the shaded region, this is exactly Sean's question and Joe's too. In the shaded region where V hits 0, before we ever encounter large damping corrections, there's eventually this very low energy scale where the subleading term in the dispersion at energy mu, W mu squared, competes with V mu. Right? That was the irrelevant operator competing with the rapidly flowing V. And that means formally we'll always hit this scale before V gets to 0. You can estimate this scale. It's exponentially small. Okay? Formally exponentially small in the coupling. But it exists, and so we should tell you what happens beneath the scale. If you had set the irrelevant operator to 0, many of us do the RG without irrelevant operators, then you would find a fixed point all the way down to V equals 0, but I think this is a more honest thing to say. Okay? Now, above that scale, one is governed by the sort of approximate fixed point of our RG equations with V basically 0. Okay? It first competes with something here. It's characterized by Wilson-Fisher bosons and by a non-Fermi liquid with a computable order epsilon, in almost dimension, and some scaling function. And that scaling function is actually 1 at large n. This should be familiar to some of you like Sean. This is a sort of locally critical form for the fermion. But I don't know what the scaling function is at n equals 1 except by doing an order-by-order messy calculation. OK, so I'm going to finish right on time or even a little early. This is the end. The talk has devolved into some complicated figures and diagrams. So I want to just summarize the takeaway messages. First of all, the most important one is that it's Joe's fault for making condensed matter physics respectable so that I could work on it, that you had to suffer through this talk. OK. But first of all, either small v over c or a large matrix n allows you to access novel fixed points in the natural field theory for quantum critical metals, a Fermi surface coupled to a boson. Because of the nature of the perturbative flow starting from the UV decoupled fixed point, small v, if you start anywhere where the perturbation theory can be used, is increasingly good in the infrared. V flows to 0. And at very low energy, the next irrelevant operator that competes with linear dispersion then becomes important. It can cause a new behavior. It's not incalculable behavior. It's just behavior we're still studying. And we think it may well be related to something called a Lifshitz transition. But that's a topic for Joe's 80th birthday. So thank you.
Questions?
Something that's never been clear on is there any widespread belief in condensed matter that this kind of effective theory is the class of theories that describes the non-Fermi liquids?
First of all, as you know, I'm not a card-carrying condensed matter physicist. I can tell you what Steve says.
Okay.
What Steve says is there may well be a nematic critical point beneath the dome. Steve Kibelson. I'm not blaming you. But that's some kind of still debated thing. And even if so, we just heard one of your very distinguished colleagues say he doesn't believe in continuum field theory. So we have doubters at all kinds of levels for all different kinds of things. But what I'll tell you is that this is probably...
I don't believe in things that aren't the flux.
Oh, okay. Good. So Matthew is supporting me then.
I mean, the only other thing I can think of would be a non-Lagrangian non-Fermi liquid theory.
I mean, Joe, as you know, this is the dumbest thing you'd write down. It's the right universality class for the simplest magnetism, the simplest nematic. So this is the dumbest problem to study. It's much less far-fetched than n equals 4 Yang-Mills or something as a model for condensed matter. It's still maybe far-fetched. I mean, that I can't judge. This is a good question. Actually, we're using right now some techniques developed by Sean and others, the memory matrix, or at least revitalized by him and others, to compute that kind of thing. From his own work, I think that looks promising. Also, the thermodynamics looks very interesting. It looks like it gives T log T specific heat, which is interesting. But that hasn't, T log T, but that remains to be published.
What are you doing with epsilon? Are you keeping it fixed or somehow are resumming it?
Epsilon is we're leaving it fixed. It's whatever it is.
Fixed and small? So.
Yeah, it could be 0. If it's 0, you still get this broad intermediate range, but eventually the coupling's at 0. The goal eventually is probably epsilon equals 1, but epsilon equals 0 is actually physically interesting too.
So when you have V, if you just set V equal to 0, do you have any issues then at higher order? I mean, because you have a completely flat band.
No, right.
I would think energy denominators would be pretty cyclical.
That's exactly why we introduced this W operator. Okay, so as V flows towards 0, before you ever get to 0 and you have the flat band, you have to analyze the theory where these terms compete.
Okay.
And we actually see what we think happens here. I'll just tell you, but it might be wrong. It's not published, so I feel free to speculate. We think there's a change in Fermi surface topology here. So something interesting does happen. And then going forward, I could try to discover what happens.
So you can set V equals 0, and then, could you do different scaling to keep W fixed? Or,
well, no, the thing is, good. So these beta function equations that show V rapidly going to 0 are valid when you're ignoring the irrelevant operator. Yeah. So then you really have to do a much more detailed analysis. That's why I'm not just saying that. No, in fact, this Lifshitz transition won't. Yeah.
Just one other comment. I mean, it was something that always had bothered me that one took this vector, of a large number of fermions NF, and in localization theory, people had done matrix large N for bosons. In fact, sums up different classes of diagrams basically, yeah. And really, what's needed is both together.
So there's something called a Veneziano limit. I think Veneziano isn't here, where you take you have a matrix N, you have NF fundamental fermions, and you take both to infinity with the ratio fixed and whatever you want it to be. We would love to be able to solve the model as a function of that parameter. And what we believe, which seems not to be necessarily consistent with what everyone else believes, is you would actually get a rich set of different critical behaviors as you interpolated between different limits. What I know for certain is that if you take the matrix large with a fixed number of fermions, I can prove that you get this kind of behavior. We can just solve self-consistent equations for the self-energy without any RG. And at large NF, I think Joe's analysis is correct. Formally at Wheating large NF, you get this Z equals 3 story. So I think something interesting must happen in between, at least for a story above some low energy breakdown scale for both analyses.
So is your fixed point stable with respect to BCS pairing?
Yeah, that's a great question. I ignored that because I was worried about more elementary issues. As you know, BCS is exponential around D equals 3, exponentially suppressed. But I think, in fact, superconductivity is a very interesting piece of this story. I think, as I told you in Trieste, we think that in this story, there are analogs of the log squared divergences in the running of the BCS couple that you found also in QCD. And I think that it's not stable with respect to some kind of superconducting instabilities that may be stronger than BCS below 3 + 1 dimensions.
Yeah, what worries me is that you don't have a small parameter that suppresses the BCS pairing. You are in the fixed point. So what is the small parameter that stay in the exponents of the BCS?
So the only small parameters here are the ones provided by things like epsilon, right? The value of G at the fixed point is epsilon. The value of lambda is epsilon. So if you're asking about at epsilon equals 1, I'm not making any claim. I'm doing the epsilon expansion and maybe telling you about intermediate behaviors close to 0.
Any more questions?
Oh, if we put in n's, then we can solve the theory in 2 + 1 completely. No, then n suppresses it. But at n equals 1, I can't go down to epsilon equals 1. At large n, I can go all the way to epsilon equals 1. And you can, again, solve self-consistently self-energy equations at large matrix n. Yeah, that may turn on, and we had talked about this before. Yeah. Okay. He's worried about various other instabilities of the shape of the Fermi surface.
Okay. Any last question? If not, let's thank Shamit.